Hello, welcome to this learning module. In this video, we're going to have a brief overview of how mass spectrometry works so that when we come to class, we can figure out how to analyze mass spectra to actually get some information out of it. Before we can analyze a mass spectrum, though, we need to know how the instrument works and what we're even looking at. And so we're going to do that in this video here. So before we get into how it works, let's remind ourselves what we know about spectroscopy. Remember, with spectroscopy, we ask molecule questions by adding energy to molecules. The molecule responds characteristically, and we measure that response. So remember, for mass spec, we are looking at molecules, individual molecules, the energy source is electricity, electrons, electron beam. The molecule responds by creating cations and breaking bonds. And we measure the mass, the molecular mass of the cation. And that's going to be important in this video. We're measuring the mass of the cations only, not anions, not neutral molecules, not radicals, but cations. All right, so that's just an overview of what we're doing with mass spec, the type of question that we're asking. What kind of molecule are you? And the energy source is an electron beam. All right, so before we get into how it works, what is mass spec good for? What do we use mass spec for? We can use it to determine the molecular weight of a molecule. Usually, we'll come back to that later, but usually we can determine the molecular mass of a molecule. We can use molecular mass to confirm the presence or the absence of certain elements. Not all elements, but certain elements. Specifically nitrogen, bromine, and chlorine, and some functional groups. Not many functional groups, certainly not all functional groups, but some functional groups we can get an idea about in mass spec. And with a little bit of math, we can get a first approximation of molecular formula. How many carbons, how many hydrogens, how many oxygens in the molecule. It'll be a first approximation, and we won't know for sure if it's the right molecular formula, but we can get an idea of a couple of plausible molecular formulas. So overall, what is mass spec good for? Not much. We don't get a lot of very specific information. We get a lot of very broad, general information, but not a lot of specific information. Instead, it really gives us an umbrella overview of the molecule. What kind of molecule am I looking at? What are the parameters of the molecule? What kinds of things can I more or less rule in and rule out so that when I go on to IR and especially NMR, I have an idea of what kind of molecule I'm looking at. It gives us a good first background look at the molecule to guide our journey through the rest of the spectra that we're going to be looking at. So I'll go ahead and say now that when I look at a new mass spec, I spend about a collective 30 seconds looking at the mass spec because I'm not getting a lot of information out of it. We'll go through exactly what I'm looking for a little bit later. But just because I'm introducing mass spec first does not mean it's the most important, and we should be spending most of our time on it. In fact, quite the opposite. This is just our introduction to the molecule, and we should really only be spending a collective 30 seconds on looking at the mass spec, checking off a couple of boxes, and then moving on to the more interesting, more useful spectra. All right, so how does a mass spec work? This is a general overview of mass spec. There is a lot of physics that goes into mass spec. There's more than one kind of mass spectrometer. We're going to be looking at just this kind of mass spectrometer. It's not the most sophisticated, but it is a way to get an overview of how mass spec works. If you go on to take an instrumental analysis course, then you'll get into a lot more detail about how mass spectrometry works. But let's remember, spectroscopy works by adding energy to the molecule. The molecule absorbs some of that energy and responds, and we measure that response. Again, a rough overview of how mass spec works. So you have your sample, and with that sample, you inject the sample into the mass spec, and it passes through a beam of electrons. Actually, if you put your ear close to the mass spec, you can hear it. It goes pew, 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 pew. No, that's not true. You can't actually hear the electron beam, but that would be cool if you could. So the molecule passes through a beam of electrons, and when that happens, so we have our molecule, and we pass it through a beam of electrons. Now, the molecule, whatever the molecule is, has some kind of electron cloud around it, of course. And when you pass the molecule through this very high energy beam of electrons, we're talking very high voltage, we'll pass it through a very high energy beam of electrons. At some point, one of those electrons will try and collide with one of the electrons in the electron cloud of the molecule. And when that happens, the electron from the molecule is ejected. So we end up ejecting an electron from the molecule, which results in a molecule that is now one electron short, which means it's a cation. And by losing that electron, the remaining electron is now unpaired. So we have both an unpaired electron and a cation, and we call that a radical cation. It's a radical because it is an unpaired electron, because we ejected one of them, and it's a cation because it's now missing one electron, so it has more positives than negatives, so it is a cation. It's otherwise the exact same molecule, just its electron cloud is missing one of the electrons. Which electron? Doesn't really matter, it's not important, but one of the electrons gets ejected when the molecule passes through that high energy electron beam. The molecule is now a cation, it's now positively charged, so the next thing in the mass spec after the electron beam are some negatively charged accelerating plates. So the negative charge attracts the positive charge of the radical cation and accelerates the cation through the instrument into this tube. So I mentioned before, mass spec only measures cations, and this is why. Cations are the only things that are positively charged, so they're the only ones accelerated through these focusing plates. And it goes into this curved tube. Now, it should just go straight through and hit the end of the curved tube. Except there is a magnet surrounding the curve of this tube. And when you have a charged molecule, it can be deflected by a magnetic field. So the molecule goes to this curve in the tube, and the magnet deflects the charged molecule. Really light molecules get deflected a lot. Really heavy molecules don't get deflected very much. Really light molecules get deflected so much they end up hitting the wall on the side over here. Really heavy ones end up hitting the wall on the side over here. But one molecule with exactly the right mass will get deflected at exactly the right angle to make it through the exit slit and into the collector and be detected. Now, that makes it seem like this is kind of limited, though you need a different mass spec for every single molecular mass, for every molecule of every weight, in order to determine what the molecular mass of the molecule is. It seems like you'd have to test every mass one by one. We obviously don't do that. So what we do is this magnet here at the curve is not a permanent magnet, but it's a variable magnet. You can change the magnetic strength of the magnet. So if you have a really light molecule, when the magnet is relatively weak, that will deflect the really light molecules perfectly to make it to the detector. If you have a really heavy molecule, when the magnet is turned up to be very strong, it will deflect the heavy molecule just the right amount to make it through the detector and get detected. So what you do is you insert your sample, you create the cations, and then you sweep through the magnetic field strength. So first the very light cations will get detected, and then over time the very heavy cations will get detected, and you can use that to measure all of the masses of interest in the same run, in the same analysis. So we can do that. We don't need a separate mass spec for every mass. We can sweep through the magnet field strength and detect all masses at the same time. So that's generally how it works. Insert the sample into the instrument. It gets bombarded by a high energy beam of electrons, which ejects one of the electrons from the electron cloud of the molecule, creating a radical cation. That radical cation gets accelerated, and when the magnet is the correct strength, it deflects that cation perfectly through the tube to hit the detector, and we detect it in our readout. So this is what the readout of a mass spec looks like. This happens to be the molecule vitamin C. So one thing that you might be asking yourself is, why are there so many peaks on the x-axis? If the molecule lost an electron and is now the radical cation, shouldn't there only be one peak for the mass of the molecule? And the answer is yes, kind of. So remember, we have our molecule. It gets hit with a high energy beam of electrons. It ejects an electron from the molecule and creates the radical cation. The thing is, this radical cation is highly unstable. It's unstable because it's a radical, and it's unstable because it's a cation. And it's so unstable that if it can, it will decompose, it will decay to become more stable. And what happens is a bond in the molecule somewhere will break and create two fragments that are smaller than the original molecule, a left side and a right side, if you will. So we create fragment number 1, and that might be a cation, and fragment number 2, and that might be a radical. If you're interested, we call these fragments daughter ions, derived from the original molecule. And those fragments each have their own molecular mass. Now, the molecule may break at several different places, so you might get several different daughter ions of varying mass, and so that's where you get some of these peaks. Now, again, mass spec only detects cations, so whatever the radical side is doesn't get detected, but only the cation side will get detected. And that will actually be somewhat characteristic for some of our molecules. But just keep in the back of your mind, remember, we're only detecting cations. Now, the other thing is, these daughter ions, let's say this radical, let's say the cation, fragment 1 cation, these daughter ions are still unstable, and they may decay even further into further ions, another cation and some other molecule, some other fragment neutral. We don't call these granddaughter ions, we just continue calling them daughter ions. But the point is, the original molecule can fragment into one or more daughter ions, and then those daughter ions can themselves fragment into even further daughter ions. And so you can imagine we can get lots of peaks in a mass spec depending on how often and where the original molecule fragments. So that's why we get so many peaks in the mass spec. Don't worry so much about every single peak. It is not a good use of your time to try and figure out what every single peak means. You could, but it's not a good use of your time. Not every peak is interesting. Not every peak is important. And I'll help guide you to figure out which peaks are the ones of interest and which ones we should be focusing on. All right, so what are we looking at in this mass spec readout? The x-axis is the molecular mass of the molecule. That's technically not true. It's technically, if you look down here at the bottom, m over z. So m is the mass and z is the charge. So it's technically an m to z ratio, a mass to charge ratio. But for our course, the charge will always be +1. We're always going to be detecting +1 cations. So it's mass divided by 1. So we can essentially say that this is the molecular weight on the x-axis. That's a fine way of thinking about it. The y-axis is relative intensity. What does that mean? When these molecules fragment, they don't fragment equally. Some fragmentations are more stable than others, and so they will happen more often than others. Molecules want to be as stable as possible. The ball always rolls downhill, so it will always follow the more stable fragmentation pathway. It will usually follow the more stable fragmentation pathway to preferentially form one daughter ion over another. So one daughter ion will always be the tallest. In this mass spec, it looks like it's this one, and that tallest one will always have a relative intensity of 100, and the height of all the other peaks are scaled relative to that one. So what does this tallest peak mean? It's called the base peak, which makes it seem like it should be really important, and it's really not. All it means is this was a fragmentation pattern that was the most productive. That's it. It's not really characteristic other than that. So don't get too hung up on which the tallest peak. That's not the most important part. Okay, so what are we looking at? Again, we start with our original molecule. We've marred it with electrons. The molecule ejects an electron from the electron cloud, and we end up with the radical cation that may fragment further. So it should stand to reason then that there should be nothing heavier, nothing with a molecular mass higher than the original molecule, right? We can fragment into things that have a molecular mass smaller than the original molecule, but there shouldn't be anything with a molecular mass greater than the original molecule. So the way we look at mass spec is we focus on the cluster of peaks furthest to the right. and the tallest peak in that cluster furthest to the right should correspond to the molecular mass of the molecule, usually. We call this the M plus peak because it corresponds to that cation that corresponds to the original molecule. And if you look at the x-axis for this one, it looks like it's 176 AMUs. And I do use AMUs specifically here because, again, we're looking at individual molecules. Remember, mass spec looks at individual molecules. In bulk, we would say grams per mole, and it's fine to say grams per mole, but technically we're looking at an individual molecule, so we're looking at AMUs for our units here. And that's what we see for vitamin C. So the mass of vitamin C is 176 AMUs. And if I zoom in on that region, that cluster of peaks furthest to the right, I do see the peak there at 176. When we look at any of these fragments, some of these fragments will be characteristic, and so we will look at some of them. When we look at these fragments, what we often do is we take the difference between the original molecule and the mass of the fragment. So the mass of the base peak looks like 105, 110, 116. This looks like it has a molecular mass of 116 AMUs. I don't know if that's interesting or not, but let's pretend that it is. And my molecule has a mass of 176 AMUs. So that's a difference of 60 AMUs. There's a 60 AMU difference between 176 and 116. So the way that we talk about these fragments is we often talk about it as an M minus 60 peak, meaning that my original molecule, my original vitamin C molecule, when that molecule fragmented into a daughter ion, it lost a fragment of 60 AMUs, and the resulting cation had a mass of 116 AMUs. Remember, we are only detecting cations. So the original 176 AMU vitamin C molecule, however it fragmented, looks like it lost a fragment of the molecule where the mass of that, the molecular mass of that fragment happened to be 60 AMUs, and the resulting cation left over, the daughter ion cation left over, looks like it has a mass of 116 AMUs. So this notation, M minus number, is often how we refer to daughter ions. And so we could do that with any daughter ion that we wanted to. Again, not all of them are useful, but we'll figure out how to, which ones are useful as we go through. All right, so when we look at this molecule of vitamin C and we zoom in on the M plus region, again, we can find the tallest peak. That's our M plus peak, and it corresponds to the mass of the molecule, 176 AMUs. And I said earlier that there really shouldn't be anything heavier than the molecule because all we're doing is ejecting an electron from the molecule. We're not adding anything to it. But if you notice, there are these two peaks down here. They're very small, but they are there. So why? The last thing we're going to talk about in this video is what those peaks mean. Why is there anything heavier than the molecule? And it has to do with isotopes. So if we look at carbon, carbon has 6 protons, 6 neutrons, 6 electrons. Electrons are massless, so they don't add to the mass of the molecule. But protons have a mass of 1 AMU, neutrons have a mass of 1 AMU, and so we get the mass of carbon to be 12 AMUs. And if you look at the periodic table, what you see on the periodic table is that the mass of carbon has a molecular mass of 12.011 grams per mole. And the question is why? It should be exactly 12. Protons, by definition, have a mass of 1. Neutrons have a mass of 1. So why do we get 12.011 grams per mole? And the answer is isotopes. So there are 3 kind of naturally occurring flavors of carbon. There is carbon-12. That's 6 protons, 6 neutrons, 6 electrons. And there's carbon-13, which is 6 protons. The number of protons defines the molecule, so 6 protons has to stay the same for carbon. But carbon-13 has 7 neutrons. The number of neutrons determines the isotope and the molecular mass of the element, and still 6 electrons. The electrons still don't add to the mass, don't account for any of the mass. So the 6 protons and 7 neutrons give us an atomic mass of 13 AMUs. There's also carbon-14, but it's radioactive and it's very trace, and so it doesn't really impact our analysis here at all. So what does this mean? There are 2 naturally occurring flavors of carbon, carbon-12 and carbon-13, but they do not occur in equal abundance. If you were to take a random scoop of carbon out of the universe, it would not be a 50-50 mixture of carbon-12 and carbon-13. In fact, carbon-12, the natural abundance of carbon-12 is about 98.9% of the naturally occurring carbon in the universe. If you were to take a random scoop of carbon out of the universe, 98.9% of those carbon atoms should be carbon-12. And about 1.1% of those carbon atoms should be carbon-13 in that random scoop. So if you were to take a random scoop of carbon in bulk, you can't really say that the atomic mass is 12 grams per mole, because some of them are carbon-12 and some of them are carbon-13. And so that's where we get the concept of the weighted average atomic mass. And the way we figure out the weighted average atomic mass and where all the masses of the atoms on the periodic table come from is we take the atomic mass of one of the isotopes, so carbon-12 should have a mass of 12, and we multiply it by its natural abundance in the universe. So carbon-12 is 98.9% abundant, so we multiply it by 98.9%, or 0.989, plus the mass of the other isotope, 13, and its natural abundance. So 1.1% would be 0.011. And we add those together, and if you put that in your calculator and you add them together, you get 12.011 grams per mole. So that's where we get 12.011 grams per mole on the periodic table. It's the weighted average of the different isotopes based on the isotope's weight and its natural abundance in the universe. If you were to take a random scoop of carbon in the universe, 98.9% of them would be carbon-12, 1.1% of them would be carbon-13. In bulk, then, we can say that the weighted average atomic mass of carbon is 12.011 grams per mole. All right, that's all well and good, but what does that mean for mass spec? Now remember, mass spec doesn't look at molecules in bulk. It looks at individual molecules. And an individual molecule either has carbon-12 or carbon-13. So 90.91%. So it looks like 1 out of every 100 atoms of carbon should be carbon-13. Vitamin C only has 6 carbons. So there might not be any carbon-13 at all in the molecule. It's very unlikely there's any carbon-13 in the molecule. But every now and then, one of those carbon atoms will be carbon-13. And when that one carbon atom is carbon-13, vitamin C as a molecule doesn't weigh 176 anymore. Now it weighs 177. So when we get this molecular mass of 177 here, that's because one time out of 100, one of those carbon atoms happened to be carbon-13. And what about the peak at 178? Well, that's even rarer. It's even smaller than the 177 peak. That's probably where there's 2 carbon-13s or something under it. Doesn't really matter. The point is it's very rare. So what does all this mean for you? What it means for you is you can ignore these smaller peaks. All it does is tells us there's carbon in the molecule, and sometimes those carbons are carbon-13. So characteristically, what does it tell us? It tells us that the molecule contains carbon. But we're in organic chemistry. Every molecule should contain carbon. So it does tell us something. It tells us the molecule contains carbon, but we kind of knew that anyway. That's the whole point of being in this course. So for our purposes, we can acknowledge that, yes, there are some peaks greater than the molecular mass, where there really shouldn't be, and those arise from the natural abundance of carbon-13. We can feel safe and secure that we are back in organic chemistry, and then we can ignore them, focus on the M+ peak, which again is the tallest peak in the cluster furthest to the right, and we can continue our analysis from there. So for now on, you can just ignore those small peaks to the right of the M+ peak. All right, that is all for our overview of mass spectrometry. In class, we're going to look at how to analyze and interpret mass spec and actually do some useful things with mass spec, like determining isotopes and other functional groups in molecules.